All right, well, hi everyone. Thank you so much for coming today to our ERI Premium Lecture. We're really excited to have Dr. Nathan Gould here today with us. I'm just gonna go ahead and give a short bio description of his work so that we can get to know a little bit more about him before he gets started.
You don't have to read it all.
Okay, so some basic information. Dr. Nathan Gould is a director at the ABS Group of Extreme Loads and Structural Risk Division. He has been practicing engineering for over 28 years. He has over 28 years of experience in design, construction, and rehabilitation of major structures in all of the regions in the United States. He's done various types of work, and he has done reconnaissance as well, which he will take a moment to talk about it towards the end of his presentation. And so I think with that said, I'll just hand it over to you and you can just describe your work from here on.
Great. Thank you, Laura and Ahmed and everybody else that's part of the organizing group. I appreciate you asking me to speak. Excited to be able to chat with you all today. So one of the things I'm going to talk about a bunch of different things, but the first part is, of course, you get to hear a little bit about ERI. And most of you obviously know a lot about ERI, so I'm not going to spend a ton of time explaining what it does, but I will tell you why I really enjoy ERI. You can see some of these things: the Freeman Family Visiting Professional, the competitions, the travel grants, learning from earthquakes is an excellent program. And then, of course, they give you this membership deal. So when you are a student, basically you get the first year of young professional membership free, and then you get the next 4 years reduced. So all really wonderful. What I really like about ERI is that, coming from a structural background, it gives me the opportunity to engage and to learn from engineers that do other things than what I do. So I belong to a lot of structural organizations, SEI and some of these other organizations. So you hear other structural people talking all the time, or if you're at geotech, you hear other geotechs speaking all the time. But what's great about ERI is that it's this group of individuals with mixed backgrounds. So not only geotech and structural, but then you have the social scientists as well, which is tremendous. And I've actually learned a ton from some of the social scientists that I've worked with and been around, and even on the reconnaissance. So that's what I really, really like about this organization. It's really a one-of-a-kind organization, extremely worthwhile, and it's excellent for advancing your career as you move forward, especially if you're really focused on earthquake engineering. So today I'd like to talk a little bit about multi-hazard design. It's really gained in popularity over the last 10 years. We have clients and owners, both private and public, that are looking for engineers, structural engineers, to help guide a team that not only can look at seismic design or an enhanced wind design, but also other things like blast and some other types of design. And it's often the experts from the seismic field that take the lead in that, because we've kind of been doing some of this a little bit longer than some of the other disciplines, if you will. So I'll talk a little bit about integrating, and then just do a real simple example project to show how the integration would take place. So let's talk about multi-hazard design. So multi-hazard design basically is natural and man-made hazards. So first we have the earthquake, the wind, and the snow. And yes, we typically already design for these in some manner, shape, or form. We have tornadoes, we have hurricanes, we have flood. With the change in climate, flood and hurricanes and even tornadoes are becoming a very large concern. We see a lot of folks asking about the potential for designing structures for these types of hazards. And then we have also these man-made hazards. So we have what we call blast or explosion. Progressive collapse could be thought of as maybe a part of that, although typically we frame progressive collapse as threat independent. And from a blast standpoint, you have man-made, but you also have accidental. So blast has been around for a long time, not just the terrorism side, but also we have petrochem issues that have been around for quite a while in terms of designing for those loads. And then, one of the things I want to talk about is, where do you find these? It's one of the first things I faced when, kind of got into some of this. And it's like, well, I know where to find seismic and conventional loads, real familiar with the ASC 7 and all that, but these other loads, where do you find these and how do you integrate them? So for conventional loads, I'm sure most of us are familiar. We tend to rely on the IBC. I would actually say, thank goodness, having practiced for quite a while in different parts of the country, it's really nice to have a single code that governs the entire US, as opposed to the 3 different codes that we had at one time. And of course, the IBC refers directly to ASC 7. So now we're on 716, soon to be 722. And from this, we can get our conventional loads. So, dead and live, and the earthquake and wind, and some other loads. So most engineers, most structural engineers, practicing structural engineers realize that, they understand this. They have this down, hopefully. What about our unconventional loads? So, like it's mentioned, we're being asked to design for these, or at least offer an opinion as to what the potential hazard is and what the implication is to the structure or to the facility. And so where do we go to find this type of information? So first, let's just talk about extreme wind. Extreme winds become more and more of an issue, not only in hurricanes. We see more hurricanes that make landfall with greater strength, but we also see a lot more tornadoes. 10 years ago, approximately, we had some really horrible tornadoes in the Midwest, through Missouri, Alabama, and some other locations that caused significant loss of life. So there are these guidelines for extreme wind. One of them is an ICC 500 document, which is an excellent document. And that's nice because it's an ICC document. So it's the same family of documents as, the building code, basically. The ICC produces the International Building Code. So there is that continuity with that. FEMA has a great document, FEMA P361, that offers a lot of excellent advice, resources, guidance on the design of safe rooms for tornadoes and hurricanes. So it's not strictly for safe rooms. A lot of the information could be applied elsewhere, but it is interesting to note how safe rooms are making their way, the requirement for safe rooms are making their way into the code for certain structures. Some of you may have seen that for schools. So tornadoes, I know they're not so prevalent on the West Coast, but a large swath of the US is exposed, and we use what we call the enhanced Fujita scale. So a lot of people still refer to it as the Fujita scale, but actually it's been quite a few years since the National Weather Service changed it and made the enhanced Fujita scale. And you can see the types of damage. And what I find interesting about this is it reminds me a lot of the MMI scale that we use in seismic, right? Where basically we make qualitative measurements, or we take, did you feel it, right? What do you feel? So it's a qualitative measurement or a qualitative idea. And from that, we back calculate. So, with MMI, we look at the types of damage and the types of ground motion, and we back figure the MMI. With the Fujita scale, it's the same thing. Basically, because we don't have the ability to measure these winds everywhere a tornado is going to occur, we look at the types of damage. And there's actually crews that go out, folks that go out after tornadoes, looking at the damage to ascertain what the wind speed might have been. That's pretty cool. If you ever have a chance to hear a lecture about that, I strongly recommend that. So these are the types of damage. You can see parts of the country. So there's, California, no, thank goodness. But there are large parts of the country, and there's some parts that are exposed to, you have extreme wind, you have seismic. So here in the Midwest with Memphis and some of the other locations, South Carolina and up north, they get both wind and seismic. But you can see that it's a pretty decent swath of the country. On the hurricane side, so this is mostly the East Coast and the Gulf region, hopefully people have seen the Saffir-Simpson scale. So it's been around for quite a while. Again, it's different than the tornadic scale in for many respects, but one thing is that we know the hurricane's coming, right? We can see it. The National Weather Service gets out there in their airplanes, and so they can measure the wind speed. So the wind speed is a fairly accurate measurement. The storm surge that's associated with them takes a little, it's a little, I won't say it's not accurate, but I would take it with a grain of salt, plus or minus, if you will. So these are the things to understand, Saffir-Simpson, the EF scale. Just as clients ask about designing for extreme wind, in addition to perhaps seismic or other hazards, these are types of things that you have to have in mind. So not only with the hurricane is the wind speed, but storm surge can be a huge deal. So if you're, if you're on the coast and you have a significant structure, storm surge may be a major threat. So this is, right out of the code. This is where we see the extreme wind. And you can see even the standard design speeds are pretty extensive. So it's something to understand. I know when I started out in the West Coast practicing, it really wasn't something on my mind, but now people tend to practice all over the United States or all over the world, in fact. So it's something to be aware of and to understand how to apply it. One of the things that's interesting about wind, and it kind of, I won't say it's totally analogous to the non-structural issue with seismic, but it is a secondary type of discussion, and this is windborne debris. And basically, these are these little missiles, or sometimes not so little, that become flying hazards during extreme wind, both tornadoes and hurricanes. So this table, you can see to meet this requirement for windborne debris, you can see the types of wind speeds, okay, and what we have to test for. Typically, these are tested items, what we test for both a vertical and horizontal surface. So it's kind of an interesting idea. So this is a 15-pound piece of 2x4 that we want. Typically, it's a facade. It could be including the window and the remaining facade of the structure. We would want the facade to basically be able to withstand this type of projectile. So to give you an idea of what that might look like, I'm not going to play all this, but I just know, I don't know if you've ever seen these tests. They're pretty cool. I know some researchers that do this. They really love these little cannons. So it's a 15-pound 2x4. So we'll see here, the first one is wood. Okay, so it's wood and siding, not a huge surprise, but what I find interesting is this test, right? So this is a brick facade. So this is somebody's home or somebody's business or somebody's office, basically a brick facade being impacted by a 2x4 traveling at speed. So interesting idea. It's something that I had never really given a lot of thought to when I first started doing extreme wind design, but it's an issue that when you have to design for that, finding a facade that will meet that requirement can be challenging. Okay, so a couple of the other hazards. Blast, again, there's what we would typically call the terrorism type risk. But a lot of it is also petrochem, it's industrial. So every year when you see the news, there's several explosions every year. And I mean, and this is, it's been going on for a while. It's been actually getting better. There's a lot of government agencies that have been focused on trying to reduce and to learn from past experiences. But it's something that we still worry about, and in often cases we design for. So in anti-terrorism force protection or blast design, the very first thing we focus on is standoff. So for those of you that maybe have looked at some of the dynamics, you know that the pressure and impulse produced by a blast lead, is a function of the distance to the third. So distance, we always say we say distance is our friend. So the more distance we can get, the more standoff we can get, the better or the safer we feel. If you are asked to do some blast work, or at least to integrate blast into your design, there's a couple of publications that are basically standards, or in the GSA's case, it's more of a guidance document for GSA. ASE has a great blast standard, blast protection of buildings. And then the GSA, again, is progressive collapse. The DoD has a similar type progressive collapse guidance as well. So this is the Unified Facilities Criteria. So for those of you not familiar, a lot of the information that's generated here in the US that focuses on ATFP and blast comes out of the defense industry. And the Unified Facilities Criteria is a great resource, and it is open, so it's public knowledge. Most of it is. There's some that is kept, a little bit more tightly held, but it's an excellent resource. And then the book on the right, I would highly recommend. In fact, for our staff, if they want to start, if we have a design and they have never been exposed to blast design, it's probably one of the first publications that I give to them. In that it really is an easy to use, easy to understand, kind of a first, a primer, if you will, on blast resistant design. So even though it says petrochem facilities, it would apply to other types of threats as well. So it's an excellent primer for those of you that may be looking at that type of work, or sometime in the future that may be asked to work on a project that has that type of design. So what is a blast? And I know that I found out earlier that most of you are graduate students, or if not all, so most have had probably dynamics. But so this should look real familiar. Basically, it's this pressure disturbance caused by sudden release of energy. And again, people tend to talk about high explosives because that's what's in the news, or that's what's, on people's minds. But we see a lot of these vapor cloud explosion or pressure vessel burst type of scenarios, especially in the industrial and the petrochem. And so, with the blast, of course, we get this very, very, very quick, in milliseconds, this very quick duration, right? And typically we have a positive phase and then we have a negative phase, which is different than most types of loads that we have. So even earthquake, right, which is a dynamic load, is so different in that the blast happens so quickly that the load is over and then the building is responding, or the structure is responding. And so it's a different arena, and it takes a little bit getting used to. And what you'll find is, if you do get into that work, is that explaining that even to other engineers, to other structural engineers, and being able to integrate that into a design can be really challenging, because sometimes the language is not quite different. So for instance, if you have 5 PSI of blast load, some people just want to multiply that by 144 and apply that to the building, as basically a static load, which is, way overkill, and would result in just a tremendously over-designed structure. So things like that are basically one of the issues that you'll face. Just to give you an idea of some of the characteristics that we talk about, this is a high-speed video, and what we're looking at is this shock wave. So I'll play it one more time, but you can see how the shock wave basically propagates out in a fairly semicircular, it's spherical, right? But it's since it's on the on grade, you only see the top. So we'll take a look again, and you can see the wave front as it propagates out very, very quickly. So it used to be, in order to understand blast and to get the characteristics and to do design and do verification, we had to do basically a lot of free field testing, which is expensive, can be dangerous, and there's other issues with that. Now we also have another approach. We have this element on the bottom that I'll talk about in just a second. So we see some of the single degree of freedom. That's our kind of our classic go to standby SDOF system. We use a lot of multi-degree of freedom software and systems as well. And there's some very high-tech computational fluid dynamics programs now that are just excellent, as well as the finite element. So you see some of that. Typically, this is FEA on the right. The bottom left, that's what we call a shock tube. And that's kind of a newer type of test facility, if you will. It's been around for a while. This one is actually something that we own. And what this does is basically allows you to put a window or a door or some other type of element here at the wide end. And basically you create a lot of pressure and then you break a diaphragm. So you pressurize it, you create it, you break a diaphragm, and then as the pressure is released, basically it will impact your element with a pressure that's somewhat similar to an actual blast pressure, but there's no explosive. So you can see that it's a nice alternative to actually being out in the field and having to go through that. And yeah, the last is testing. Testing can get really expensive. I mean, it's kind of cool. If you have an opportunity to be there to witness it, I'd highly recommend it. But it's fairly expensive, and sometimes, you know, you get results, and it's like every other type of testing. You know, you're never quite guaranteed of what you're going to get. So this is just, you know, there was a lot of discussion about CFD when it first came out, how well it would simulate the blast loading. And so this is just a comparison of the CFD and the blast loading. So what we can see is that on the left is the actual loading, and on the right is a CFD model. And so we can approximate the blast loading pretty well using CFD. So it's a nice thought. It's nice to have, because it's really helpful to have that alternative from an analysis standpoint. So progressive collapse, it was not born, but it became hugely important to the US and to others really after Oklahoma City. So for those of you maybe a little bit younger, this was back in April of '95. And most of the people were actually injured due to the flying glass and debris. But one of the things that came out of this tragedy was the recognition that some buildings are prone to progressive collapse, where basically you have an element or elements that when they're removed, like a transfer girder, for instance, that causes disproportionate collapse throughout the structure. And this became widely recognized and understood as being an issue. And so now certain buildings for certain clients are designed specifically to resist progressive collapse. As I mentioned, one of the biggest hazards coming out of that tragedy was flying glass and the debris produced by the flying glass. And so on the left, we see, this is kind of a witness panel or a test panel. On the right, you can see some glass that's been strengthened actually, where one of the things is it's not only the glazing and the frame are strengthened to resist the blast loads, but then those loads have to go somewhere. So you wind up with very stout jambs and sills and heads around the window. So just to give you an idea of what this looks like from a test standpoint. So if you are inside the structure and the blast is outside, you'll basically see what happens. First, this is a pane of glass that is not laminated or strengthened against blast loads. So here comes the wave, and you can see all the shards. So that's one of the issues that we're highly concerned about when we start designing in this environment. Okay, so that was a quick tour of the other loads, if you will, the multi-hazard and the blast, you know, the wind. But of course, this is ERI, so we need to, you know, we're all about seismic. So I wanted to, you know, talk a little bit about the seismic and how we integrate that in. And so seismic, you know, of course, we have the new buildings with the IBC, and then referencing ASC 7, and of course, you know, performance-based design, ASC 41, extremely popular in certain circles. And I have that little arrow because I know there's always this discussion about if you design a new building per code and then you check it per ASC 41, will it check out? And, you know, there's been a lot of discussion about that. So I find that interesting, if not amusing sometimes, but I think that could be an entirely separate topic. So again, standard codes, most of us are familiar with those. We have the IBC And then it references the ASC 716. And from that, we're told where to go find our seismic maps, the seismicity, and then of course, the materials, the different disciplines are also referenced. So there's a lot of referencing going on. And I think for students, especially, and even our younger engineers, it can get confusing on which code to use and what is the correct reference. So, you know, sometimes you do run across instances where people are using, for instance, seismic maps that are either too old or too current, if you will. It doesn't really make sense, but are not correct based on what ASC 7 is being referenced. So we do need to be careful with that. So again, building codes, you know, we think of these as a minimum set of design standards. I would say most practicing structural and other engineers even understand this to some degree. A lot of other disciplines as part of the consulting team, probably not so much. So, you know, it's important that we be able to articulate this clearly and make sure that everybody understands what we're talking about. So again, it's about life safety. And we anticipate the structural and non-structural damage. And as I'm sure that some of you have seen or have talked about, you know, this can be a foreign concept for some folks, and a lot of owners and even architects that you work with, they're not aware that this is actually, you know, something that can result from a well-designed code building. So again, no financial consideration. So if the building is a complete economic loss after an earthquake, but everybody gets out safely, the structural engineer, he or she may be patting themselves on the back saying, hey, look at design per code. We did a great job. Everything performed well. We had all this plastic deformation, a lot of energy absorbed, but hey, building still, you know, everybody got out. We did a great job. And then the owner is saying, well, hey, but my building's a loss. So there is this issue. You know, in the code, we can talk about doing a little bit better. So this is from, you know, this would be like an IBC ASC 7. Of course, ASC 41 is slightly different, but from a building code standpoint, we can bring this out and have a little chat about these importance factors. But typically this doesn't really come up unless you're actually looking at a hospital or a fire station, or perhaps a school or a large assembly facility. So, you know, we have critical facilities. Most of us are aware of that. A huge hospital program in California, of course, and elsewhere. But outside the hospitals and maybe some other special structures, we don't tend to think of critical design. And again, you know, how do we avoid economic loss? Okay, this is really important to many, many owners. And they may not articulate it well. And sometimes you have to talk to the right part of the ownership. So for instance, if you're doing a very large facility, you may be talking to their construction management folks or some type of contracting arm that they may have. And it's really the risk manager that is really focused on this business interruption and the market share. So all of that is key. But again, you have to talk to the right folks and have a clear message. So lately, we've been hearing a lot about enhanced seismic design in terms of resiliency. And then also there's been this excellent publication on functional recovery. And these are two very hot topics. And you know, definitely worth, I would recommend taking a look at that in this publication on the right. What this really, you know, it's really takes off from the idea of this performance-based design. So performance-based seismic design has been around for a while. And so I tend to think, and I think a lot of folks do, that earthquake engineers, we're typically the leaders in performance-based design. So I didn't say seismic, I just said performance-based design. So when it comes down to designing structures to perform at a high level for other hazards, who better to get that message across and to guide the team than an engineer that really understands, you know, the history, and basically that history being performance-based seismic design. So some older slides that been around for a while, but find helpful sometimes, that, you know, why don't we rely on the code and have this discussion quite often, not only internally, but a lot of externally with our team. and different owners. And sometimes it's a long discussion, and you have to respect the owner or the leader of the team to, it's their typically their foot in the bill. So you can guide them to the idea and help them understand what it means and what it doesn't mean. But at the end of the day, it does become their choice. And you want to focus on their expectations, right? And appeal to their economic, their economic issues, and basically help them focus on, what things could be like after an event. So again, to protect their investment, we don't typically want to rely on the building code as the base design if we can avoid it, and make this a team effort. So if it's just the seismic engineer pushing for this, it looks a little self-serving, right? Because this means that we're going to do more work probably. And B, it's typically going to fall on deaf ears because nobody else really wants to hear about it after the fact. So you have to get everybody together early. And I mean early, like when they're actually still thinking about how they're going to budget for this new project. Once the budget is set for a project and things are moving forward, it's almost too late, because then enhanced seismic or enhanced wind or whatever it may be, then that becomes a burden to the project and to the ownership. So currently, a lot of us are using ASCE 4117. It is an excellent resource for seismic. We actually also use it for other hazards as well in certain fashions. One of the things we do is we use it to help delineate different performance levels relative to hazard or return periods, and talk about how to control the building performance, or at least understand building performance and the expectations. So what we like to say is there's fewer surprises if there is an earthquake, and that surprises to the design, to the ownership group especially. In the end, we really feel like it adds value to the overall process if it's done correctly. So this is a slide I'm sure some of you have seen. And again, we use this not only for seismic, but we use something similar for other hazards as well, so they can understand where they are in a basic design and then what their options are going forward. So for instance, this photo on the left is actually a chip facility, like a microchip or a silicon wafer type facility. And some of you may remember that, in Taiwan, there's some very large earthquakes in Japan, Taiwan, and some of these facilities suffered huge losses just daily. So some facilities, it could be, they could be out millions of dollars every day they're not producing. So it's a huge issue. And so, yes, the design may go up a little bit in terms of cost, but when you balance that against the potential for loss, that doesn't look so bad. So again, I'm sure may have seen this before. So we tend to focus on the basic safety objective for our typical building, but really for more important buildings, we try to push the ownership group towards the enhanced objective. So this is kind of another old classic slide, been around for a while, but I kind of like it to help. I use it to help the staff, students, to talk about life safety versus the higher performance levels. And really, you go from life safety, where basically we think of that as like, either a red or a yellow tag post-event, where basically the building's a loss, to these higher levels, immediate occupancy and operational, where the really only difference is it's the non-structural, right? So both buildings can be, you can go in, you can occupy them, but you really can't work or have function in a building where there's no utilities, there's no lifelines. So the operational really encompasses the non-structural as well. Speaking of the non-structural, it's one of the issues that we see over and over again in different earthquakes that are critical, that often lead to a building not being functional after an earthquake or an extreme wind event. And it's one of those elements that are often forgotten about or not really focused on during an event, and during a design, excuse me. So, we try to, non-structural it's become more of a known quantity, if you will, but a lot of times you'll get to ends of jobs and people will be kind of looking to see who dropped the ball in terms of non-structural, not getting braced, not getting anchored, not getting laterally restrained. So one of the things that we try to do, as a structural or seismic team member, is to make sure the team understands that this is something that has to be taken care of. So, is it a structural engineering issue? Is it a mechanical engineering issue? If it's ducting, or is it an electrical issue? If it's MCC units. So, when you're a team, you have to make sure the team takes care of it. And so that just needs to be something that's focused on during the design process. So all is not lost, or all is not bad news. We have a lot of great advanced technologies, and I'm sure many of you have seen. One of them that's really popular these days are these buckling restrained brace frames. There's several others as well. So, I think the future is really bright as far as tools and options for using enhanced seismic, and installing these types of advanced technologies, not only in new structures, but in some cases, existing structures as well. So I think there's a lot of future, a lot of bright ideas out there, and a lot of good ideas. So I think there's a lot to look forward to. We always get asked about cost. I mean, that's one thing that always comes up. So what does it cost to upgrade to better seismic performance? And it's really tough to pin it down because a lot of it depends on the overall project, right? If it's a small project where the structural work is a significant piece of the whole project, then it may be more percentage-wise. If it's a huge project with all kinds of MEP and different types of equipment, mechanical, whatever, the structure could be relatively small from a cost perspective, and so the total cost could be pretty small. So, but tend to kind of focus in on these ranges. But again, it really fluctuates. So you can see, these are very close. The difference being, again, is the lifelines and the non-structural. But this could be as high, I've seen it as high as 7 to 10%, if for a smaller project where, again, it's a complicated structure, and the structure and then the bracing and the enhanced bracing or restraint of the equipment drove the cost up. So again, it's really a little bit all over the place. Okay, so that was kind of a quick tour of some of the other hazards along with kind of the seismic performance base. And the idea is to tie it together. So you have a bunch of different hazards. You have the potential at some sites to actually have multiple hazards at one time. So how do we kind of pull it all together? The first thing we do is we keep the load cases separate. So we don't want to mix and match hazards. So it sounds really simple, but when people get busy, things get a little crazy. Things can get mixed up. So it's really important from a bookkeeping standpoint to really focus on the different loads, because there's different issues, different load factors, different V factors, et cetera. So we have to keep everything nice and neat and nice and separate. Be very clear about code versus ultimate design. So for instance, seismic, most wind, we're in a code design, whether it's ASC 7 or 41. But when we go to the blast world, we might be in an ultimate design with no load factors and, a fee of 1. So it's important to understand the type of design regime that we're working in and how to apply that. And of course, owner education. That is a huge issue. Without the owner being educated and on board, things very rarely tend to go well. And same as the last bullet, this coordination with the disciplines. Whether it's this enhanced seismic or the other hazards, often some of the disciplines won't have been involved in that type of project before. So this could be totally new to them. So, you may have an MEP engineer that's never done, a high seismic job or a job with blast or maybe both. And so you're going to have to actually help educate and help guide a little bit to make sure that everything gets done correctly. And constructability. Constructability is a huge issue too. It can be one of those that can make or break the project from many perspectives. So real quick, simple little example. This is a 911 facility in St. Louis County. Basically it was designed to handle all the combined 911 response and emergency response for the county. So, I don't know, so probably close to, over 1 million, between 1 and 2 million people. So it's a pretty important structure. And they had a lot of requirements. They wanted a high seismic design. And we talked about whether to stick with the code or go to, at this time, it was probably ASC 4113. But we did stick with the code for some other reasons. We did use an occupancy category 4, so an IF 1.5. They wanted a tornadic wind design of 180, and then they wanted blast criteria per the DoD. So the extreme wind was interesting because about 10 years ago, almost 10 years ago exactly, there was a pretty large tornado that came through the area, damaged the airport, and actually damaged a lot of the structures and facilities near this, where this new 911 center was going. So they had asked, in light of that, as the design was progressing, how could they integrate tornado? And, we started having a conversation, and, you say to them, well, how big do you want? And they say, well, how big does it come? What's the biggest? And you say, well, there's this EF5, which is like the Kansas Dorothy thing. And they're like, oh, that's great. And you're like, no, that's not so great, because it's hard when you get to the very extreme levels to find products and find design elements that will actually work, from warranty issues and other things. So we actually settled on that 180 mile an hour as kind of a compromise. A lot of the emergency responders, first responder type folks were really focused on anti-terrorism force protection. They really wanted to have this facility to the extent that they felt safe and secure. You can see that we basically use enhanced standoff, right? This distance is our friend from a blast perspective to provide more standoff and reduce the pressures from a blast perspective. But you can see this is a glazed storefront, and you can see the size of the mullions going in here. So this, you have the gentleman for comparison. These are some really huge steel tubes, relatively speaking, that you would not normally see for this type of storefront, which are basically designed to take the blast loads that are imposed on the glazing, which is not yet installed, and then it'll take it out to the remaining part of the structure. Constructability was a huge issue. The contractor in this job had never done high seismic, nor had he done blast. So we had situations. The one on the left is just a headache for the engineer. The one on the right is more of a nightmare, where you're like, oh my gosh, where do we start? So, out in California or in high seismic regions where you do a lot of seismic, hopefully there's contractors that really understand, especially with rebar placement and things in congestion. But this was a tough hill to climb. So in summary, multi-hazard design is increasing. So if you go out into the consulting world or the AE world, there's a pretty good chance that you might be asked to design some type of structure or structures for different hazards. Designing for one hazard does not cover all hazards. So you often will get that question, and you'll say, and it's a serious question that a lot of times architects or owners have. They'll be like, well, we're high seismic. Doesn't that cover me for blast? Or, I designed for blast, so I'm good for wind, right? And it's not quite the same. And so you have to be patient when it comes to that. And really what we're seeing is that the earthquake professionals are typically we're being looked at and asked to provide leadership because of the maturity of earthquake engineering. So, as we see this change in climate and other things going on, and this more focused idea of resiliency and functionality, it's the earthquake engineering community, I think, that's really being asked to step up and to really take a lead in some of this. So, and then constructability. No matter how good your design, how great your design is, it really doesn't matter if the construction is not good. So, we can pat ourselves on the back all we want on our design, but if the construction doesn't go well, that's all folks will remember. And then lastly, a final plug for ERI, just a great way of getting involved in the earthquake community. I found it to be a great organization throughout my years of practice and highly recommend it. And this last picture actually is from the ERI recon team out in New Zealand. And I know if we have time after this, we can go through and talk a little bit about that reconnaissance as well. So I'm happy to take questions on this right now, or we can also go to the reconnaissance if you prefer.
Yeah, I suggest maybe questions first and then,
sure.
You know.
Absolutely.
Laura, yeah, go ahead.
You can go ahead and put it in the chat, or you can also unmute yourself and just ask away.
But just get things started. I mean, you know, Nathan, so I mean, it's great that you covered all these different hazards. But when, you know, in practice, you know, what is it that you observe as being the driving force if you want to design for more than one hazard, like wind and earthquake, or you know, or blast and something else? You know, is it primarily cost, or are owners willing to invest more if they can get a better performance of the system?
You know, it's so owner dependent. Some owners, it's all about cost. And so they want to, you know, so, you know, out in the, you know, different regions where we have different seismicity, for instance, you know, not so everything's not high, but we have this transitional seismicity. So like some parts of the West Coast and Midwest and so forth. Some owners will even shop around with the geotech. So all the geotech folks on this will appreciate that. But I know they'll shop around to get the right soil type, you know, the site soil. So then they can get the right seismic design category and not be, you know, seismic design category D. So they don't have to do much for seismic. So you have those type of owners for sure that are really focused on cost. But the right owners, or a lot of owners who really are designing, number one, are building to inhabit their building. So they're not developers, but they're designing, so they're going to inhabit that building. And they care very deeply, not only about, they care about their employees, but also whatever they're producing within that building is almost irreplaceable. And they can't, you know, tolerate significant downtime. So those types of owners, it flips, right? So cost is a little bit less of an issue, or a lot less of an issue. And then it's about performance. So pretty much, I like to say you can pretty much kind of tell where that owner is going to fall, just understanding their business, but sometimes you're surprised, you know, but a little education can often help as well. The problem is once, if it's a large facility, often those are budgeted for several years in advance, right? They do like a capital plan. So if you're going to, you know, if there's a huge new chemical facility being built in a high seismic zone, and the risk manager is saying, you know, she says, hey, we should do better. You know, we don't want to be out. If we're out every day, we're out, we lose X millions of dollars. We need, you know, a higher level of performance. But what happens if, you know, they budgeted for this, you know, 3 years ago or 5 years ago? So they already have basically their design and construction budget. Then an enhanced seismic design would blow that out of the water. So and so you face that resistance, right? So the risk manager or the CFO might be like, hey, this is a great idea. We need to do this. But the folks on the capital side or the construction management side who maybe have been given that task to adhere to the budget are like, well, you know, wait, we can't do that. It's going to blow our budget, or it's going to blow our schedule. So even within organizations where it makes a lot of sense and you think it would be a no-brainer to do enhanced design, whether seismic or wind or something else, you'll find that at different levels of the organization, you'll find advocates, but you'll also find people that are not real helpful. So, yeah.
Okay.
I would have a follow-up question from, I guess, the real world perspective of, are those conversations happening as they're putting like a request for proposals? Is it after you've submitted the proposal? Is it while you're in the middle of the design that you're trying to convince them of this?
So not to be overly flippant, but I would say yes, all the above. And as you go down your list, as the further you go down your list, the harder it is to gain traction, right? So if we can have this conversation, so we work with certain architects typically, or other folks, and they know us, and so we can have a conversation and say, look, have you talked about this, or this is, and they may even have that in their mind. If you respond to an RFP, request for proposal, it's a great time to make that point. Some owners are receptive. And then again, some might say, well, we can't really afford to do that. That's not within our budget, or that's not what we've allocated for this project. But you never know. So we typically will try at that point for sure, if we can. Once you're already in the design phase, that is the most difficult, because basically, that ship has sailed, and you're kind of like, wait, we should have this conversation. And everybody's like, well, no, we're moving forward. And I mean, I can't count the number of times, we've wanted to have that conversation. And like I said, certain portions of the owner is not usually one monolithic group. It's made up of different people often. And so, sometimes you'll gain traction on one, but not the other. So it becomes really difficult once you're in the design phase. If you can have that conversation prior to the RFP being issued, that's the best possible scenario. So it's just difficult, because a lot of times as structural engineers, we're not typically thought of as being involved at that point of a project, right? When an owner thinks of the beginnings of a project, they're talking to maybe a developer, but they're talking to an architect, they're doing some initial planning, and the structural engineer is not really part of their thinking. And so we try to change that as well. Sometimes we succeed, sometimes we don't.
Thank you.
Sure.
I have a question.
Sure.
I'm really interested in hearing about the different responsibilities in your group, because you do plats, you do wind, you do seismic. So are there people who focus on each one, or does everybody work on all of these hazards?
That's a great question. So we have people that prefer to do certain hazards and certain focus. We have like a blast center of excellence down in San Antonio, where we have that shock tube and we do most of our testing, but we also have people elsewhere that do a lot of blast work. The way it typically works is, if someone comes to me and says, I really would like to be involved in this project, typically because they want to learn how to do a certain thing, we'll find a way for them to get involved. If someone says, I prefer just to focus on seismic, or there's some blast engineers that all they want to do is blast, that's their thing. And so we don't mandate cross training. Typically, I mean, there's some engineers that they have such great potential that we feel like that they would be a huge positive in certain areas. We might try to push a little bit, but it's typically the other way. So people will say, hey, I'd like to be involved with this type of project. And sometimes, it's different in that you can't always accommodate right away, because you may be busy with other work. So they already may be spoken for in terms of their work, but we try to accommodate that. But yeah, it's a good question. So I think, my personal perspective is to try to learn at least how to do at least enough of everything, so at least that they're familiar and understand what goes into it. They don't have to be an expert in everything, but I'd like for them to at least learn, what it takes to get from here to there. Yeah, good question.
Thank you. Does anyone have any other questions related to the presentation before we ask Nathan to please talk about the reconnaissance? All right, so in that case, feel free to go ahead and start. Okay. And then I'll start recording again right before you start. Oh, never mind, I'm still recording.
All right, can everybody see my screen?
Yep.
Okay, great. So this won't be nearly as long. I was asked to talk a little bit about earthquake reconnaissance. I know a lot of folks, it's a fun topic. So I'm not going to go through this whole presentation. I'll get bits and pieces. I was very fortunate to be part of the team, the ERI team that was in Christchurch after that earthquake. You know, you can stop for a second. It was a pretty big earthquake, but the last part really is I won't say the most important, because the dead and injured are certainly important, but the impact to the New Zealand economy was major. So from a seismological standpoint, there's a fault that runs through New Zealand, the Alpine Fault. New Zealand has a North and South Island. And basically this earthquake happened in Christchurch off the main fault. So this was kind of like maybe like a zone 2A in the old zone speak, you know, that zone 2B. So they were waiting for the big earthquake that happened in some of the other cities that were right on the fault. And Christchurch they had seismic design, but not nearly the same level as some of the other cities. So here you can see some of the PGA information. There was a first quake was a 7.1, and then the 6.3 was a very damaging earthquake. Here's the epicenter, and then the city center, and then here's this port of Littleton is an extremely important port for Christchurch. And for those of you not familiar, GNS is very similar to our USGS. And then you can see the propagation of the main fault and actually the aftershocks, basically in an east-west trend. So I'm kind of blowing through a lot of this very quickly just because of timing, but you can see, you know, here's their design spectra, right? And then here's some of their ground motion. So you can, I mean, it doesn't take a lot to figure out that they were well above their typical design spectra. And when you talk about their retrofits, even more involved, because they had different retrofit levels depending on what the engineer had chosen. I do like this slide because it shows basically the ground accelerations. And what I really like about it is it shows this huge vertical component that I think we don't design for it really. I mean, okay, we have that like little 0.2 SDS that we kick into our load equations, but you know, this is basically showing that there is vertical acceleration over a G. So we saw large pieces of equipment that had basically bounced across the floor, which was just really incredible. So the amount of vertical acceleration was really surprising. So, you know, again, it was a surprise. Wellington was the city right here that was waiting for the big one. And, you know, basically this is more of a moderate type seismic region. So here's our team. Again, it was really interesting in that there was a bunch of us that were seismic or structural, there was geotechs, and then there was a bunch of social scientists as well. So it was a really neat group of folks. So I'll kind of walk through some of the damage. You can see some classic masonry damage. We tend to see this every earthquake. This is some damage I think that was unexpected. So for those of you that may be familiar with New Zealand, they have some very, very famous concrete professors or concrete folks that come out of New Zealand. And, you know, pretty proud of the concrete design. So it was a little surprising to see the level of damage that we saw, some really poor ties and confinement. So somewhat not surprising when you see some of the design. Some really typical pier failures in the URM and a lot of short column failures. So, you know, nothing where we would be overly shocked. This was a little interesting. These were eccentric brace frames. So this is 10 years ago. You know, eccentric brace frames have been around for a while. I don't know if a lot of them had been through a bunch of earthquakes. And of course, you know, with eccentric brace frames, we expect some damage here in the link, remember, where basically we expect some plastic hinging to go on. But what we saw were these basically fractures right here that were taking off from this outside gusset. So definitely not a failure mode that should have been anticipated or should have occurred. You know, we saw these type of failures. These are regular geometry, masonry piers, 16 inches and ties at 16. So no great shock. One important lesson that we took home with us, that I took home, was these retrofitted URMs. So, you know, we've been retrofitting URMs. I mean, I've been doing it since, you know, I basically started working. And one of the ways people had anchored into unreinforced masonry was what we call screen tube anchors, right? So these are tubes, kind of like mesh tubes. So you drill the hole in the masonry and you shove the tube in, and then you fill it with grout, and you put the anchor in, or not grout, adhesive typically, excuse me. And, you know, it's basically this bulb of adhesive restrains the anchor from pulling out. And what we found was that it performed really poorly throughout the area. So these are all retrofits. These are all seismically retrofitted structures that failed. So, I mean, like the very first thing that I did when I came back was with my office, basically said, no more screen, the screen tube thing, we got to take another look. And even if that meant, you know, cutting the face shell off a masonry block and filling it all up with grout and putting in a more traditional anchor, at least that way I would feel confident in the performance. So this was a huge surprise how poorly these retrofits performed. Historic was a big issue. They call them heritage. We would call these historic. And there were huge fights about whether certain historic buildings could be demolished. And, we'll probably see the same thing. So a lot of light industrial damage, and I won't spend a lot of time. Things that we see all the time, you see in California after every earthquake, tilt ups or precasts where basically you have anchors that have failed and we lose a panel. Here you can see the anchor and the failure where basically it just pulled away from the foundation. And again, some more types of anchor failures, and they actually come back and have to shore in order to keep the building stable. And tons of non-structural damage everywhere. So, we saw everything from piping to conduits to ducting, but this is the machinery I was talking about. These things weigh 25,000 pounds. And the first thing we walk in this place, and the first thing the guys want to talk about is how these were bouncing across the floor during the earthquake. And, we're like, oh, did you run outside? Did you take cover? Did you hide? Oh, no, we wanted it. And this is before everybody had camera phones. So I'm sure they would have been taking video if it happened today. But they were all really excited to have explaining what they witnessed. So it was, I'm sure it was exciting. But vertical acceleration was a huge takeaway. Glazing, we see this every earthquake, so it's not surprising. It's very difficult to design glazing well. That can take a lot of displacement. Contents, again, not typically thought about or considered, but again, it can make getting out of these buildings really difficult. And if it's your life savings tied up in some type of storage or stock, it can be an issue. Classic damage to palletized racks. We see this every earthquake. So, these racks are always a mystery, right? Because, you have this like little pseudo brace frame in the transverse direction, and you have this kind of a moment frame in the longitudinal direction, right? I mean, technically they design as a moment frame, but it's a pretty light moment frame, I guess is to say, and so that was an issue. Now we did see some well-designed, non-structural. This is actually some telecon equipment that was well braced. It's interesting though, and then this building is that they had some old masonry partitions, and the building did pretty well, but masonry partitions, as you would expect, had a lot of cracking and so forth. The building wasn't going to collapse. There was no issue, but the workers who worked in this facility, they saw the cracks in the masonry partitions and said, we're scared. We think the building's going to collapse, the next big aftershock, so we're not coming to work. And this is before telecommuting. So, the business was in a bad way. So it is important to understand that employee perception can mean a lot. And if the employees aren't comfortable, even if it's not a life safety issue, if they're not comfortable coming back to work, then they may not reoccupy the building. So one of the things I wanted to really focus on was this case study to kind of illustrate what non-structural means, or what kind of damage can happen to a facility or a business due to non-structural. So this is a carpet manufacturer. It's kind of a classic New Zealand facility in that they take wool and basically produce yarn, and significant damage. And the real issue is that they had to let 220, most of their workers were let go after the earthquake, because even though the structure had damage, there was no major collapse. So they had these little funky brace frames, these little turnbuckles, but the structure was still standing. It was a non-structural, and they had a lot of precision machines. So these machines were very highly calibrated, and the parts are very special, not easy to repair, very long lead time. And so these machines were damaged, and that basically put the folks out of work. Non-structural, we had really large displacements in some of the equipment, and also we had all this non-structural where basically, I think a lot of this could have been repaired fairly quickly, but the machines themselves were the long lead item. And then we had a lot of other things going on. We had a lot of collapsed masonry, and we had the sand all over the place when you first walked in, and we realized that they had suffered significant liquefaction. So a lot of the machines were on special isolated pads, if you will, and a lot of those had basically either been popped up or pushed down or moved due to some of the liquefiable soil underneath. And then we also had this the site issue as well. So how am I doing for time? The last issue I want to talk about, because I think it's really relevant to pretty much any earthquake, is this inspection. And so when the ERI team arrived, the access to the city center was limited. And we also found that there were 70,000 buildings to be inspected. And they don't have a ton of engineers in New Zealand. So several of us volunteered to be part of their rapid assessment program, or to participate, to help out for a couple of days. And I think that was extremely rewarding, at least from my perspective. So this is the Emergency Operations Center. It was pretty chaotic, but I will say that they did a great job in trying to get things, keep everything straight. I'm assuming we'll see much of the same going on, when there's a large earthquake here in the States. This is they had a cordon basically, so they used mostly police, maybe some military. Honestly, I can't quite recall, but all the access was controlled. So they basically did not want, tourists, if you will, wandering up and down, taking pictures or looking at the damage. So this is like one of the teams that we all went out in teams. And these were these guys, these search and rescue guys, that they wouldn't let us go out without them. And so one guy always stood outside the building. I guess if something happened, if there was an aftershock and we got buried, he could go run and tell everybody where to find us. But so it was good. But the real takeaway was their use of the ATC 20 methodology, which is important. This is the current methodology. ATC, Applied Technology Council, uses the ATC 20 methodology for post-disaster or post-earthquake inspection. So many of you may be familiar with the green, the yellow, and the red tags. And so they actually did a modification to that, which was really interesting. And they added some additional categories. And you can see here just the sheer number of buildings to be inspected. So it was quite a few. And they were all over the place, right? So 1 minute you're inspecting, 5-6 story concrete frame or concrete shear wall. The next minute you're, some kind of strip mall, and then you're at somebody's house. So the house was really tough personally, because usually the commercial buildings were vacant, but the houses, usually the people were still there. So, if you tag a house yellow or red, you're basically telling them, where red is no entry and yellow is conditional entry, you're basically telling them that they're going to have to vacate their house. So that was unexpected in terms of having that kind of interaction. And then, this is actually historic structure, and there was a lot of protests that were going on about, the idea of demolishing some of these, they call the heritage buildings, the historic. So that was a very quick 15-minute tour, but it's important because it's a moderate region. So, it's more like a Sacramento, St. Louis, Memphis, maybe Charleston type area, moderate seismic design, and maybe not quite ready for a major earthquake. The modern structural system saw quite a bit of damage, so it was a big surprise. Really disappointed in the performance of the retrofits. A lot of important information out of that. And then the non-structural, I think that's a lesson we already knew, but saw it again. And then the post-earthquake evaluation. So anyway, so I know I had that 15 extra minutes, so hopefully I didn't run over. I'm happy to take questions on this as well, if any of you have any.
I know a lot of you are actually meeting Nathan later, but if you have any questions specifically about the reconnaissance work, you can go ahead and ask them now.
I have a question.
Sure.
So thanks for this presentation. This was super interesting as well. And you may have mentioned it and I just missed it, but how did you end up on a team that went to New Zealand?
So it's a good question. I was pretty active, or I am active with ERI. And, after the event had happened, there was discussions about putting a team together, and they were taking some volunteers. My company at that time, I can't remember, they made it clear that I could have that time to go and be part of this team. So it was just an opportunity, it's basically they were soliciting volunteers really from members that they knew that, were interested in this type of work, that did this type of work, but they were also looking for a cross section, right? So not just structural, it was structural, geotechnical, and also social science. So it was lucky. I was fortunate, but it's part of being part of an organization like ERI, where basically you have that, you can find opportunities like that. So I was very lucky. I was able to go to Haiti, not with ERI, as part of a small NSF team. It was night and day because of the types of construction and so forth. But so from an opportunity standpoint, a lot of times you may need to be proactive if if something like this happens and you want to be involved. It pays to be proactive and to reach out.
Thank you.
Mm-hmm.
I think there's a question in the chat for you. They're asking, do you think we're learning enough from past failures in reconnaissance? How hard is it to make changes to regulations based on more local cases and case histories?
That's a good question. I would like to say that we are learning. I certainly hope we are learning. Sometimes I question whether we learn the right lessons, or whether we learn the same lessons over and over again. I do think that we learn, about different things from different earthquakes. So for instance, right, after Northridge, we learned certain things. After Loma Prieta, Northridge was, we had all the steel issues and everything going on. So there's certain takeaways, but I think those same things keep coming back over and over again. I think the non-structural is one thing that we don't seem to learn really well. And I think part of it is because it's not something that really belongs to one discipline, right? So when MEP guys, when they do their work, they're primarily responsible, but they don't really know how to do some of the anchorage and restraint. So I think that tends to fall through. And I am concerned that sometimes we don't learn that lesson. So it's a good question. Hopefully we learned something. I definitely learned about some of the anchorages and retrofit